Okay, we will move to our next question. Okay, so I hope you can see my screen. Okay, so 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 I'm going to do this question 2 of mid-sem exam. Okay, it's also easy question. Okay, and you can see that question 3 I'm not going to do here because we have already done this. No, this is time shifting property. I think you can remember that. Okay, so we have derived that, we have proved the time shifting property in one of our tutorial session. Okay, and I think this one also we have done in our class. Okay, so we have to use the duality property to uh, find the Fourier transform of this signal. Okay, we can directly do it, but the integration is somewhat difficult. Okay, so we can use duality property easily and uh, find the answer for this. We can find the Fourier transform or time domains, the frequency domain signal of this signal easily. Okay, so here also I'm not going to do this. Okay, and this one also I have discussed. No? This one also I have discussed how uh, this two pulse, how this uh, how this two pulse. One pulse is a narrow pulse, and other is the wide. Is a wider pulse. Okay, so we have discussed how the bandwidth. What is the bandwidth requirement and how this pulse width affect to the bandwidth of the channel, communication channel. We have already discussed. Okay, so the third question, all the parts we have discussed in our tutorial session. So now I'm not going to do this. Okay, and so we will do this one. Okay, question 2. Okay, so you can see that we have to draw the signal. Okay, we have done this in several times. Okay, it is a sinusoidal signal. Okay, it is very easy question also. So anyway, I can write it. So the question is that draw xt a cos omega naught t plus theta general sinusoidal wave. Xt a naught cos omega naught t plus theta. So you already know that this is angular velocity, this is phase shift, and this is amplitude. Okay, so if we draw a sinusoidal, the cosine wave without a phase shift, okay, it will look like this. Okay, it will look like this. Okay. And this is one cycle, and this is another cycle like this. The signal will look like this. Okay, but you can see here there is an arbitrary phase shift. Okay, so we have to show this phase shift here. Okay, so you can see that this phase shift we can't tell it is plus or minus phase shift. Okay, so that phase shift may be shift to here, this way, or other way. Okay, okay, so we don't know how much the shift is, so we can use arbitrary shifting. Okay, like this. We can say it is like this. Okay, okay, and this is a naught. Okay, and this is a naught. Okay, so you can see that if you consider this one and this one, that is a circle. Okay, that is a circle here. Okay, so I think this sketch is enough. Now we haven't much information to draw the complete signal, but this information is enough, and this period will be 2 by omega naught. No, this period. You already know that this is a sinusoidal wave, and the fundamental period is 2 by omega naught. So this is the period. So I think that information is enough. Mark that is information in your drawing is enough. Then you will get full marks. Okay, and then uh, then we have um, okay. So we have to find the Fourier transform of this cos signal. Okay, and we are given a fact. Okay, so if you going to evaluate the Fourier transform of this xt, okay, so you know the procedure. Okay, so you know the basic procedure, the principal approach. You have to find the integration. You have to evaluate this integration xt into e to the power minus j omega t dt. So this xt is a cos signal here. Okay, cos signal here. Okay. So that way you can try to evaluate it. So this cost function is here, and here the exponential terms is there, and using the Euler formula you can divide this into two. Okay, into two exponential terms using the Euler formula. Then sometime you can easily evaluate the integration. Okay, and you can find the answer, the time domain signal of this cosine wave. Okay, but we no need to follow that steps. Okay, because we have given one fact, known fact. Okay, that. Okay, so we have given one known fact. What is that? Sorry. So you can see that this fact is given. Okay, so we can use this fact. Okay, so can you think? Can you think a way of apply this fact to this question, to this problem? Okay, so we are given this Fourier transform, no, e to the power j alpha t Fourier transform we are given. Okay, and we have to apply this fact to find the Fourier transform of this signal. So how can you relate these two signal? Okay, definitely you can see that you can relate this signal, this two part, okay, to identity using the Euler formula, no? Okay, so here also you can use the Euler formula. So already you know that, okay, we can express this xt. Okay, I will. Okay, so this is the first one. Okay, we have already done, and now we are going to evaluate the Fourier transform of xt. Okay, so xt is a naught cos omega naught t plus theta. So this is the signal, sinusoidal signal. We have to find that this is time domain signal. We have to find the Fourier transform. Okay, we have to find Fourier transform. That means x omega, capital X omega. We have to find. Okay, So you can see that, okay, we are given one fact, that is we are given that E j alpha theta, the Fourier transform is 2 pi delta 2 pi delta omega minus alpha, 2 pi delta omega minus alpha, right? Okay, so this signal, this exponential signal Fourier transform is already given. Okay, so we can use that fact to find the Fourier transform of this signal. Okay, so you can see that this fact, this term and this term, you can find a relationship with using the Euler formula definitely, no? So you have xt, okay, then you can find the Euler formula. You can use the Euler formula to cos function for this cos function, okay. So you can write it as a naught e to the power j omega naught t plus theta, okay, j, okay, omega naught t plus theta, okay. So if this is theta, okay, so consider this as theta, okay, then we can write it as e to the power j omega theta plus e to the power minus j omega naught t plus theta. This is divided by 2, no? So is this correct? Okay. So we know that we can write ej theta as cos theta minus I sin theta. So we can write ej theta as cos theta plus I sin theta. Okay, e minus j theta as cos theta minus I sin theta. So if I add these two, I will have e to the power j theta plus e to the power minus j theta is equal to 2 cos theta. Cos theta means we have divided this by 2. Okay, so this term we have. So I consider this full terms as theta. Then we will have our expression like this, no? Correct? I think you can understand it, okay? So a naught by 2 e to the power j omega naught t plus theta e to the power minus j omega naught plus theta. This one j theta and this is minus j theta. So here we have minus and here we have plus. Okay. So now we have finally used the Euler formula and you can see that this theta term is a constant. Okay. So using basic mathematics, we can write this as here e theta, no? So I can write it e j theta e to the power minus j omega naught t plus theta. So, sorry, now theta is not there. So plus j omega naught t, okay, plus e to the power minus j theta e to the power minus j omega naught t. Right, okay. So now you can see that we have write this in terms of this terms, the exponential terms. Okay, so if we find the Fourier transform of this xt, okay, so we have to find the Fourier transform of xt. Okay, so I can find Fourier transform of this part, no, this part, whole part. So a naught by 2 is a constant, so I can get it out. Okay, so a naught by 2 is here. Okay, so here we have e to the power j theta e to the power plus j omega naught t, okay, plus e to the power minus j theta e to the power minus j omega naught t, this term. Okay, so you know that using linearity property of Fourier transform, we can write this as separately, this Fourier transform, this total Fourier transform, here we have a plus value. Okay, so we can write it separately, using the linear property. Okay, so a naught by 2, I will write this one separately. So I have f e to the power j theta e to the power plus j omega naught t. So this is a constant part. So again, I can get it out. Okay, so I get it out. E j theta. Okay, I get out. So I have this term a naught e j theta by 2. Okay, and here I have Fourier transform of e to the power j omega naught t. Okay, so this is one part. And here I use this one separately. So a naught by 2 is common for both terms. So a naught by 2 is there. And this one is when I write this f e to the power minus j theta e to the power minus j omega theta. So you can see that e to the power j theta is a constant. So I can get it out. Okay. So I will get it out, j theta. Okay. And I have Fourier transform of e to the power minus j omega naught t. Okay, so let's take it one by one, because I am doing this real time. So maybe some mistake can be happen. So if I make any mistake, you can tell me. Okay, then I can correct it. Okay, otherwise the mistake will continue. Okay. So let's look at the procedure again. Okay, so here x naught is equal to a naught cos omega t by t. Okay, so I have write it using Euler formula like this: e to the power j omega naught t plus theta plus e to the power minus j omega naught t plus theta divided by 2. So I have a naught by 2. Okay, then I can see that we can see that here we have two parts. Okay, and this theta is a constant value. So using basic mathematics, darshaka, using darshaka, I can't remember the word for darshaka. Okay. So anyway, we can use that darshaka method. Okay, so I can write this separately as e to the power j theta, e to the power plus j omega naught t. Same here. Okay, e to the power minus j omega t, e to the power minus j omega naught t. Okay, correct, no mistake. Okay, so this is then I will apply Fourier transform for all this expression. Okay, so I have applied it. Okay, then using the linear property, I separate the Fourier transform. Okay, I separately write the Fourier transform of each of this term. Okay, so when I write this one, a naught to and e to the power j theta is constant, so I have it Fourier transform of j omega naught here, and a naught by 2 minus e to the power minus j theta. I got nf. Okay, so I think now you can see the relationship. Okay, so you can see that we no need to do any integration, no. Okay, so you can see that this Fourier transform and this Fourier transform is given as the fact, no, as the known fact. These two Fourier transform are given. So simply we can substitute the value here. Okay, so you can see that. Okay, so you can see that here it is 2 5 j alpha t. No, we are given that e j alpha t Fourier transform of e to the power j alpha t is equal to 5 delta omega minus alpha. Okay, so this is given. E to the power j alpha t is Fourier transform of e to the power j alpha t is equal to 5 delta omega minus omega L. So let's see it again. Correct, no? E to the power j alpha theta is equal to 5 delta omega minus omega L. So we have that. Okay, so you can compare these terms and this term, no? Okay, so you can write, this term, okay, Fourier transform of this a to the power j omega t. So here it is alpha and here it is omega naught. So you can write this term as 2 5 omega minus omega naught. Okay, and here you can write this plus and this is minus omega naught. Okay, so you can see that we have e to the power j minus omega naught t. So here instead of alpha, we have minus omega naught. So I can write this as 2 5 omega. So minus here, when it is plus, minus omega naught, but here it is minus, so it will be plus omega naught. Okay, so we have this one also. Okay, so now we can write, no? So this terms we have a naught e to the power j theta by 2 and 2 5 delta omega by omega naught. Okay, plus a naught e to the power minus j theta by 2 5 delta omega plus omega naught. This here it is delta. Okay, so this is the answer, no? So this 2 and 2 cancel out. Okay, so this is the answer. Okay, so next move to the other one. Draw the magnitude and phase spectrum of x omega. Okay, so magnitude and phase spectrum of x omega. So magnitude spectrum is, I think it is the amplitude spectrum, no? Frequency spectrum. Okay, so I can write directly write it. Okay. Magnitude means that spectrum component value. Okay, magnitude means plus value. Okay, so you can see that both are plus. There is no minus one. Okay, so we have plus value also like this. Okay, so we have, if this is on 0 point, okay, if I write to draw this with respect to omega, this is 0 point. Okay, so you already know that delta function is like this, omega, this is 0 with respect to omega. Okay, so if I write omega minus omega naught, that means this impulse will shift to this way. No, here you can remember the time transformation. Okay, transformation technique. So using transformation technique, we can derive this. No, so here we have delta omega minus omega naught. Okay, and if you shift by plus omega naught, okay, this omega, then the impulse will shift to this way, minus side. Okay, okay, so if I have omega plus omega naught, okay, so here we have at minus omega naught. Okay, okay, uh, so you can see that if it is 0, okay, this is plus omega naught and this is minus omega naught. Plus omega naught is here, this signal, no, this signal, this denote the here. Okay, so it magnitude is into a naught e j theta, the phi also there, a naught 5 j theta. Okay, uh, sorry, so you can see that this is a complex term, no, this is a complex term. Okay, so when we are asked to find the magnitude, okay, we have to find the magnitude of that complex coefficients. Okay, so you can see that this amplitude is a, okay, complex one. Okay, hope you got it. Okay, a naught 5 e j theta. So this is a complex one. So we have the magnitude, this one, no, a naught 5. This is the magnitude, and theta, this is the phase. Okay, so when we are drawing the magnitude spectrum, okay, we have to find the magnitude of this complex coefficients. Okay, so I'm sorry. Okay, so this is the magnitude, no, correct? Okay, so if you have a complex number alpha e j theta, okay, so you can write it as alpha cos theta minus I, sorry, plus I alpha sin theta. Okay, so if you want to get the magnitude, you have to square this part and this part and get the square root. So when you square this, alpha square cos square plus okay, okay, alpha square sin square sin square theta. So you can see that when you get out the alpha square, you have cos square plus cos square theta plus sin square theta. So cos square theta plus sin square theta is 1. Okay, so you have alpha square, then you will get the what is called the square root, then you have alpha. So magnitude is simply alpha. Okay, and phase is simply theta. Okay, so theta is the phase. Okay, so you can see that. So if I draw the magnitude, we have for this part it is a naught 5. Okay, and here for this part it is also a naught 5. Okay, so this is the magnitude spectrum. And if you draw the phase spectrum, you have to draw the phase with respect to omega. So this term we have theta phase plus phase. Okay, so the phase, so you have in this, so here in this y-axis we mark the uh, magnitude. Okay, magnitude. But when we are drawing the phase plot, so here we have to mark the phase of this y-axis. Okay, so here for this impulse, the phase is theta, okay, plus theta, and for this impulse plus, that means here it is shifted here. For this impulse, phase is minus theta, like this. Okay, so this is the magnitude plot and phase plot. Okay, so what is the next one? Okay, so we have to find the Fourier transform of yt ntxt where message signal is empty. Okay, so it is a pulse. Okay, for the magnitude spectrum of y omega. Okay, so we have to evaluate this one. Okay, so let's see how to evaluate this. So we have the signal. We have the signal y. We have signal yt is equal to, actually this one also we have done. Okay, as I can remember, this one we have done. This is no, this is not done. No, we have done the modulation theorem. Okay, so this is not same. Okay, but we can do this. Okay, so yt is equal to mt xt. Okay, so we have to, so this yt is a product signal, no, product signal, the signal nt into xt. Okay, So we are given the MT is already given. Okay, it is a rectangular signal. So you know that MT is a rectangular pulse. Okay, so T, this is MT. Okay, so it is a pulse like this. The width is tau, no? T by tau, the width. Okay, that means we can say it is minus tau to, sorry, minus tau half to plus, like this. Okay, minus tau by 2 plus tau by 2. So this is uh, the same T. It is a pulse, no? It is a pulse. Okay. So you can see that if we if we have a product with another x omega signal, so xt is a arbitrary signal, no? It may be like this. Okay. So you can see that if we have the product, we have only these two limits, no? So we will so this minus into minus, this one part cancel, and sorry, this is 0 and this some value 0 into some value means 0, and here also 0 into some value is 0. So you will have uh, the waveform, this xt waveform, only within this pulse duration. Okay, this pulse duration is tau. So you have the xt signal only with this pulse spectrum. Okay, sorry, with this pulse width. Okay, tau. Okay, so you can see that MT, so this is 1. Okay, so this is 1. Okay, so you can see that when you multiply MT into XT, we have XT itself. Okay, so we have, okay, MT into XT. Okay, we have XT itself, but XT is exist only within minus tau plus tau. Okay, so this thing we can this point we can figure out, no? Okay, so we are given that the Fourier transform of xt is already known. Okay, so Fourier transform of xt is already known. Okay, so if I try to relate this, okay, so if I find the Fourier transform xt, normally we have to evaluate it from minus infinity to plus infinity. Okay, then xt e to the power j omega t. Okay, then I have the Fourier transform, no, x omega. Okay, but here so here we have minus tau to plus tau, minus tau to plus tau. Okay. So if you find the Fourier transform of this signal, yt signal, okay, so you have to find the Fourier transform of xt actually, e to the power minus j omega t, but the limit is from minus tau to plus tau. Okay, minus tau to plus tau. So actually, I couldn't see any relationship between this transform and this transform. There is only a minus the limit issue, but we can't reduce the limit, no. So I think the, we need some more information to solve this question. Maybe I am wrong. Okay. Anyway, I will check this. Okay, check this, and we will try to do this. Okay. So if I could find the solution, I will record this and upload. Okay. So at this point, I couldn't see any relationship between this integration and this integration. Okay, because you can see that here it is minus infinity plus infinity. Here it is minus tau to plus tau. Okay, so I think our logic is okay. No, we are fine. We are asked to find the Fourier transform of mt into xt. Okay, so mt is a pulse. Okay, rectangular pulse. So we have, it is given minus tau by 2 to plus tau by 2. Okay, and if you multiply this pulse with the with this xt arbitrary signal, so you will have that signal only within this pulse duration. Other will be zero, no? Okay, so you have the pulse. So this signal is nothing but xt itself, but the t duration is, t limit is minus tau by 2 to plus tau by 2. Okay, so if you want to find the Fourier transform here, you have to integrate the xt e to the power j omega t. Okay, xt e to the power j omega t minus here from minus tau to plus tau. Okay, so this is y omega. Okay, and you are given that x omega, the Fourier transform of x, that is minus infinity to plus infinity xt e to the power minus j omega t. Okay, so I couldn't see anything to relate this to. Okay, so anyway, I will check this. Okay, and if I could find the answer, I will upload this. So anyway, I think if you put from up to this level, it is somewhat easy. Okay, you can come up to this level, and I hope if you come to this level, you will get the full mark. So don't worry. Okay, so anyway, I will check with Dr. Udesh. Okay, how this solve. Okay, I couldn't do that. I can't see any relationship between these two. Okay, so I'm sorry. So okay, so that is the last part, no? So so I think we have done two questions. Okay. The third question, I'm not going to do this because in tutorial session, I have done all these things. Okay. So this is a time shifting property. We have verified it. Okay. And this is duality property. We have solved many question using duality property, 3 or 4 question, and before the exam I have done this, no? In the same day, at the exam day, I have done this question, the very similar question. Okay, and this one I have done before the mid-sem. Okay, so here you have to find the bandwidth requirement of these two pulse. Okay, so we have done it, and we have see how this two pulse require the bandwidth. Okay, so you can remember that this narrow pulse need more bandwidth, and this wider pulse need low bandwidth. Okay, so we have done this question T. So now I'm going to do this. Okay, so I'm sorry for that. This one, okay, because I couldn't complete it. Anyway, I will check it with Dr. Udesh. Okay, then I will let you know. Okay, so we will wind up. Okay. Okay, do you have any question?